to the third and final talk in this series. I'm still discussing arithmetic groups. And today, I'm going to start by repeating something I did yesterday. Yesterday, I gave two different ways to tell whether or not G mod gamma was compact. Today, we'll have a third version of that same thing. We'll check whether G mod gamma is compact by looking for something called isotropic vectors. I'll explain what that means. But deciding whether or not a manifold is compact is so fundamental, I wanted to emphasize it, and so I'm talking about three different ways. Then I'll use that compactness criterion to introduce something called Q-rank. I mean, isotropic vectors are related to an algebraic definition of something we call the Q-rank, and it turns out that that gives us some geometric information about what's called the asymptotic cone of our locally symmetric space. I'll explain that, and then at the end, I'll do something I probably should have done right at the start. I'm going to define what an arithmetic group is finally, but the trouble is the definition's a bit technical, and you may have noticed in the first two talks I tried to avoid anything that was anything like being technical, but today, finally, I'm going to do some things that maybe will be, too confusing to understand. So, but I'm going to explain what an arithmetic group is, and once you know what an arithmetic group actually is, the actual definition, we'll have a way of constructing co-compact lattices in SO1N. It's easy to get a non-co-compact arithmetic subgroup. Just take the integer points of SO1N. That will give you the obvious integer points. Gives a lattice. It gives you a finite volume locally symmetric. Sorry, not just locally symmetric, but it gives you a finite volume hyperbolic manifold. But you have to do something a little bit more clever to get a compact manifold, and that's what I'll do. And the key to that, the key to getting a compact manifold, is a very important technique called restriction of scalars. So at the end, we'll talk. Well, another thing I want to do today is talk about restriction of scalars. So, we're finally going to get the definition of an arithmetic group today, and we'll use that to do something that's not at all obvious. All right, but let's start out then by just talking about non-compactness, or a compactness criterion. All right, so, for example, let's let gamma be the obvious lattice that'll give us a hyperbolic manifold. Let gamma be the integer points of SO13. That's an arithmetic subgroup of SO13. So, SO13, the corresponding symmetric space, is hyperbolic 3 space. So when you take 3 space mod gamma, what you get is a hyperbolic 3 manifold. And the basic question is this compact? And we have two ways to tell. As I said, well, one way to check is if it's not compact, then there's a bunch of G's and a bunch of gammas, so that when you conjugate the gammas by the G's, the limit is the identity. That's one way to check, but it's hard to find the G's and the gammas. Another way that usually is easier is just to check whether or not there's a unipotent element of gamma. But again, I don't know, if you're not a group theorist, you probably don't want to be looking for unipotent elements of a group. So let me give you a different way to tell whether or not M is compact. And that's this proposition. If we're talking about a group like this that's defined as the integer points of some orthogonal group, which for a hyperbolic geometry is almost all that you're interested in, is groups like this, there's I don't know, I keep calling these easy, but anyhow, there's a natural way to check whether or not the corresponding manifold is compact. So let's suppose we're in the situation where we have some quadratic form, and a quadratic form is just a polynomial where all the terms have degree exactly 2. So it's a homogeneous polynomial of degree 2 in some number of variables. And non-degenerate is just a technical condition. It's just there could be some number of variables here. Non-degenerate means just that if you choose a different basis, so if you do a change of variables, you won't be able to reduce the number of variables you've got. So for example, an example of a degenerate quadratic form would be just x1 plus x2 all squared. x1 plus x2 squared is degenerate because if I just let x be x1 plus x2, then I'm just talking about x squared. So a degenerate form is one where you can make it have less variables just by doing a simple linear change of variables. But that, again, that's a technical condition. All of the forms we look at today are obviously non-degenerate, so it's not an issue at all. I mean, the natural forms that you look at are non-degenerate. Okay, so suppose we've got a quadratic form and all of the coefficients are integers. So for example, it could be something like take 3 variables and just do the natural sort of thing that a hyperbolic geometry might do. Take x1 squared. You can put some coefficients. And in fact, you're allowed to have cross terms. I could have put x1, x2, or x3, x2, or whatever. I mean, but this is an example that's just, and the point is, if you don't have any cross terms, it's obvious that this is not degenerate. All 3 variables are there, and they have to be there. If you do a change of variables, you're not going to be able to get rid of anything. So a diagonal form like this, one where there's no cross terms, is clearly non-degenerate. Well, the thing is then what we can do is make out of this, we're going to define the corresponding orthogonal group. So in this case, if this is our form Q, then this has one positive and two negatives, so G is just SO12 of isomorphism. We just count the plus signs and count the minus signs, you know what G is. And then we'll make gamma to be the corresponding arithmetic subgroup, just take the integer points of G. So now we've got an arithmetic subgroup of a semi-simple group, so definitely gamma is a lattice in G. And the key thing, though, is that I can tell you whether or not G mod gamma is compact. If it's not compact, well, it's if and only if there's a bunch of gammas and a bunch of G's, so if you conjugate the gammas by the G's, they get close to the identity. Or it's if and only if there's a unipotent element in gamma. But the trouble is, both of those conditions are hard to check. In many cases, something that's usually easy to check is just checking whether or not there exists an isotropic Q vector. And we need to tell you what that means. Isotropic just means length 0. So there's some vector, and to be a Q vector means it should be in, well, it should have, what's it? Q vector means all its entry, what do you call those? Coordinates are in Q. There's some vector of length 0, but it's not the 0 vector. That's what an isotropic vector is. An isotropic vector is what, I shouldn't call it length, but anyhow. When you put it in the quadratic form, it's a root of this polynomial, maybe I should say. If there's a rational root, then G mod gamma is not compact. This is not obvious, so I want to actually prove this. All right, so that's, I think I just copied the statement over. G mod gamma is not compact if and only if there's an isotropic Q vector. So a vector with rational coordinates whose length or whose value under the quadratic form is 0. I won't do both directions this time. Let me just do one of them. Let me just show that G mod gamma is not compact. Oh, yeah, if G mod gamma is not compact, then there's an isotropic vector. That's what I'm going to do. And I'll just say, if you want, I'll say just for a moment something about the converse, but this will give you the idea of what's going on. So the point is, I'm assuming G mod gamma is not compact, and if you're here yesterday and you're awake at the right time, then you know that that means that there's this sequence of G's and gammas I've been talking about, and it also means there's a unipotent matrix in gamma. Well, the one I want is the one I call Godemon's criterion, that there's a unipotent matrix in gamma. Right? So because G mod gamma is not compact, I explained yesterday that there has to be a unipotent matrix in gamma. And then also, I told you something called the Jacobson-Morozov lemma yesterday. That said that whenever you have a unipotent, any unipotent matrix in any group G, in any semi-simple group G, there's corresponding to that a homomorphism, a copy of SL2R inside of G, where the obvious unipotent matrix in SL2R maps onto whatever unipotent you have, maps onto you. So inside it, whenever you've got an element, a unipotent element of a group, of a semi-simple group G, along with that comes an entire copy of SL2R. That's the thing. And it's the SL2R with this unipotent being just corresponding to the obvious unipotent. Okay, that's what I said yesterday. That's what I need, except that I need a souped-up version of this. Jacobson-Morozov isn't just for groups over R. It actually works over any field of characteristic 0. And for all I know, it might work over characteristic P as well, but I don't know anything about characteristic P. So, but anyhow, for any field of characteristic 0, you have the same result. And what I need is this result over Q. So if we take just the Q points of G, there'll be a map of SL2Q into that with rho hitting U. Okay, so it works over any field of characteristic 0, at least. And that's what it is. So we've got this map onto there. Excuse me. Well, now let me just define, okay, I've got this unipotent, this guy maps onto U, corresponding to this unipotent element. Last time when I used SL2R, I looked at the corresponding diagonal matrix. I want to do that again today. I've got a diagonal matrix corresponding to U. And I'll just, you can put any number you want there. There's not 1 or minus 1, but let's say 2.5 there. And then it's a crucial fact, this is probably not obvious, but it's a theorem from the theory of algebraic groups, that because we've got a homomorphism here that's everything's happening over Q, and the original matrix here that we're applying rho to, this matrix in here is obviously diagonalizable over Q. Right? It's diagonal and its eigenvalues are rational. When you apply a homomorphism like this that maps rational points to rational points, the image will also be diagonalizable over Q. It's not obvious, I think, but it's a theorem that maps between algebraic groups like this will preserve diagonalizability. Or in the theory of algebraic groups, we call this a split diagonal matrix, or split sum is above. Let's setting up A is diagonalizable over Q. What that means is that A has a whole basis consisting of eigenvectors. Sorry, I said that wrong. What that means is that, I guess I didn't say it right, but suppose G is an SLNR. Rn has a basis consisting of eigenvectors for A. So in particular, A does have an eigenvector. And since we're diagonalizing over Q, that eigenvector has to have rational entries, rational coordinates. And the corresponding, in fact, it's got a basis of eigenvectors that are in Q, and all the eigenvalues are also in Q. Right, so it's got a rational eigenvalue. I've got an eigenvector. It's got a rational eigenvalue. But the thing is that if all the eigenvalues were just plus or minus 1, then A squared would be the identity. But if you look at this matrix, A squared is not the identity. So there has to be some eigenvalue that's not plus or minus 1. So it's rational. I guess I don't really need that. The key thing is it's some real number that's not plus or minus 1. And let me just assume, so we've got some number. And now I just want to do something that's maybe silly, but it works. I want to calculate Q of V. And let's see, and I'm hoping it's going to come out to be 0. That's the plan. I'm going to calculate Q of V, and we'll see that it's 0. Well, Q of V, the point is that A is rho of something, and rho of anything is in G, and G is the orthogonal group of Q. Anything, what that tells us is that A preserves Q. A is in the orthogonal group of Q. That means the Q of A times V is the same as Q of V. So I'm just going to apply A to V, except I'll apply it a lot of times. But I can apply A as many times as I want. It's not going to change Q of V. Right? So Q of A to the K of V is the same as Q of V, but A to the K we can calculate because V is an eigenvector with eigenvalue lambda. So A to the K of V is just lambda to the K times V. And this is just a scalar. Scalars come out of a quadratic form, and let's see if I did it right. This is homogeneous, so it should come out as lambda to 2k. Good, I got it right. All right. So, because this is a homogeneous polynomial in degree 2, so multiplying by a scalar will pull out, but it's not linear, it's quadratic, so you get lambda to 2k. And now I'm just going to let k go off to infinity. And look at what I get in the limit. Well, this is just a constant. And let's say that lambda's actually, I said k would go up to infinity. If lambda is less than 1, I'll let k go to infinity. If lambda is bigger than 1, I'll go to minus infinity. But let's just say that lambda is less than 1. If k goes off to infinity, we're taking something less than 1 in absolute value, raised to a large power, that gets very small, that goes to 0. Okay, so this limit is 0 as k goes to infinity, or to minus infinity if lambda is bigger than 1. So if you look what we've got here, I've got a number, a constant, that converges to 0. The only way that can happen is if that number actually is 0. And that's what I was trying to prove. All right, so that's the condition. If G mod gamma is not compact, then you can find an isotropic vector. And it comes from this Godemont criterion we had before. And maybe I should say, I'm not going to prove the converse. It's an exercise, but it's an exercise in algebra, not in geometry. But it's just that you can prove that if you've got an isotropic vector, then the corresponding orthogonal group does have unipotent vectors in there, unipotent matrices in there. And in fact, if this vector has integer coordinates, then you can choose it to be an integer matrix. But it's an exercise in algebra. You just have to write down once you've got a vector of length 0, you write down some unipotent matrix, some upper triangular matrix that preserves the quadratic form. Let me not do that. That's not so interesting. And it's definitely not geometric. This I thought was sort of geometric because you're looking at something converging. At least it's topological, something converging to 0. But this is crucial. The point is this condition is easy to check. Much easier for a non-algebraist, at least, to find than a sequence of gammas and g's or finding a unipotent matrix. We just have to find a vector of length 0. So, for example, let's take sort of the obvious gamma that I've already mentioned, I think, the integer matrices in SO13. Well, in that case, the corresponding manifold, I think I already said this, is definitely not compact. And one way to do that would be to find a unipotent matrix in SO13, but again, I think to a geometer that's not the obvious thing to do. It's much easier to just find an isotropic vector. Well, first of all, we have to write down, I didn't say, the quadratic form we've got here is just x naught squared minus all the other guys squared. That's the quadratic form we're looking at. And now we just want to find a vector of length 0. And I think if I gave everybody here 1 minute, that would be enough time to find a vector of length 0. Just try obvious things. Maybe let x naught be 1 and x1 be 1 and the other two 0. We get 1 squared minus 1 squared, we get 0. So this was easy, whereas if I gave everybody in the room 1 minute to find a unipotent matrix, I think hardly anybody would get there. And even worse, if I told everybody in the room to find a sequence of g's and gammas, so when you conjugated the gammas by the g's, the limit was the identity, I think you need a lot more than 1 minute. So this one finally is an easy condition to check in most cases. Yeah?
So in the last slide, how do we know that row of this A is in G?
Oh, because it says row maps into G. Was that all you're asking?
Yes.
Is that okay? Yeah, so it's just the fact that, yeah, that's part of the Jacobson-Morrisov lemma, is that whenever you have a semi-simple group G, every unipotent element you can find in SL2 contains an inside of G.
Yes,
that was your question.
Element, yes, but just A. Oh.
It's the image of row. All row of everything is inside of G.
So that's the part of Jacobson.
That's part of Jacobson-Morrisov. Part of Jacobson-Morrisov is that inside any semi-simple group, every unipotent element is contained inside of an SL2 in the group.
Yes, but A is not the image of G.
But it's image of something in SL2R. So the way to think about it is that the entire SL2R is inside of G. So you're not just, yeah, I mean, it's not at all obvious. It's not in the least obvious. But if you ever have a unipotent element inside of G, it can't be all by itself. It has to be, it's contained by a whole SL2R that's still inside of G. Now, this is an amazing theorem. It's very powerful. That's part of why I wanted to give this proof, is that Jacobson-Morrisov is something people use all the time. It's incredible. Yeah, so in particular, once you've got one unipotent matrix inside of G, it can't be the only one, because you could take, if you put a 0 up there and a 1 down at the bottom instead, that's also unipotent, so you get a completely different unipotent. If G has a single unipotent, then it's got a completely different unipotent, and plus it's got something else that normalizes both of them. No, yeah, this is saying a lot. Yeah, and they generate, yeah, the two unipotents generate an SL2. That's exactly it, yeah. Yeah, that's what the Jacobson-Morrisov lemma says. For every unipotent, you can find another unipotent inside of G, so the two of them together generate an SL2. That's the same theorem, exactly. Yeah, so it's very, yeah, it's fundamental to look for it. Yeah.
I think you can simplify the argument at the end, because if you just look at the left-hand side and the right-hand side of the second last line, so when
this one here?
equal to 1, then it is immediately 0.
So if what's not equal to 1?
If lambda is not equal to 1. And you have Q of B is equal to lambda 2k Q of B. So when lambda is not equal to 1, then this is immediately 0. You don't need all these calculations and conversion.
You know, you're right. Okay, yeah. So I made this more complicated. I mean, all week long, I've been trying to just ignore complications, make things as simple as possible. I suddenly botched up this one. Yeah, you're absolutely right. So let's go ahead and say that. Let me put you're absolutely right. Thank you. Yeah. So you don't need to. So the problem, I finally had a topological argument here. I thought it was good for this audience, but it's not. It's purely algebraic. So what's been pointed out is I should go back one. Yeah, I should go back. There we go. Yeah. Okay. So just from this equation right here, if Q of V is equal to something times Q of V, but if lambda is not plus or minus 1, then lambda to 2k is not going to be 1. I've got Q of V equals something times Q of V, and if something's not 1, the only way that just implies that Q of V is 0. Absolutely. That's absolutely correct. It's not the way I think about it, but it's absolutely right. Okay, yeah. So skip all this. Skip Q of V is 0. Yeah, okay.
But even the k anymore.
Oh, give me a break. You're right. Okay, yeah, absolutely right. So let's go back. Let's go back farther. Let's go to there. And get rid of the k. I'm sorry I can't do that, but yeah, pretend there's no k there. Oh, no, I don't. One more step. Sorry, yeah, there. Right. No. Oh, I have to go all the way to there. Yeah, okay, but absolutely right. Yeah, there's no need for k. And that also means, the other good thing is that means that even if lambda is minus 1, it would be okay. I didn't have to, yeah, so that's a much simpler way to say it.
Well, you would have to square it.
Oh, you're right. Aha. Yeah, so you're right. This was correct. So just know that there's no need for a k. You're right. Thank you. Thank you. My bad. Sorry. Yeah, actually, yeah, I call myself a group theorist. I'm not. When I'm talking to group theorists, I don't call myself a group theorist. When I'm talking to group theorists, I call myself a dynamicist, because I study group actions. And that's my problem here, is I was thinking of this as, you know, A is moving some points around. So this is the natural way for me to think about it. But yes, if I honestly were an algebraist, I would have noticed that. Thank you. Okay. But yeah. All right, any other corrections and improvements or complaints? All right, yeah, so that made it more complicated than necessary. Okay, let's go. What are we doing here? Oh, yeah, so that's what I just proved, that, yeah, at least I proved one direction anyhow. We can check whether or not the manifold is compact just by checking whether there's an isotropic vector. Oh, I already did this example too, didn't I? Yeah. Yeah, we found it was easy to find an isotropic vector in that case. But let me do another example. Instead of letting Q be just this obvious quadratic form, I'm going to change it slightly. I'll just change that first coefficient. I'm going to put something in front there. You can put a 2 or a 3 or a 4, but that's not what I want. I want to put a 7 in front of it. Okay, so let's just do the same thing, but I changed one coefficient, and it turns out that simple change makes all the difference in the world. In this case, if we let gamma obviously be the integer points, then H mod gamma, the corresponding hyperbolic manifold, is compact. Just changing the 1 to a 7 goes all the way from some terrible manifold that a topologist doesn't want to think about, although geometers don't mind it so much, to a beautiful compact manifold. That simple change there, and let me explain why. The proof, it's not difficult, but the unfortunate fact, which happens all the time in arithmetic groups, is that you need some number theory. To understand arithmetic groups, you're talking about integers, just fundamentally, so you have to do... Oh, shoot, no, yeah, there's a minus sign there. So actually, now I understand, I think the notes might be right. At some point, no, notes are wrong too. I remember at some point when I was looking through, there were 2 minus signs, and I deleted one. Oh, you've got 2 minus signs. Oh, that's the top. Yeah, well, one of them was supposed to be over there. And I got rid of it because I realized there shouldn't be 2 minus signs, but I didn't realize I put it in the wrong place. Okay? Yeah, so this is supposed to be, that's not a quadratic form, what I've got written there, because you need everything in degree 2. Yeah, so all I want to do is I want to just change the 1 to a 7. Sorry, yeah, there should be a minus sign right there. Yeah, it's a typo that I didn't catch. Yeah, I caught that there was I said, I don't want 2 minus signs there, so that's what the notes say. That's what I fixed. I didn't realize there was a mistake somewhere else, too. Okay. Yeah, so in this case, the manifold suddenly is completely different. It's a compact manifold, and the proof, as I was saying, is that we just use some number theory, and the number theory is that 7 is easy to check, is not a sum of 3 squares. 1 squared plus 1 squared plus 2 squared is a little too small. 2 squared plus 2, just try, and you'll never get 7. The trouble is that doesn't prove what I need, but it's a fact that 7 is not a sum of 3 squares, even rational squares. Okay, it's obviously not a sum of 3 squares of integers, but it's a fact from number theory that it's not a sum of 3 squares of rational numbers. Okay? And so, if you think about it, suppose we had except that it's, when you look at it, it's wrong. But if 7x squared minus these guys, well, this is subtracting off the sum of 3 squares. If this were 0, then 7 times something would be a sum of 3 squares. If you just bring this to the other side, you know 7 is a sum of 3 squares that has a denominator. X not the denominator. Okay? If there was an isotropic vector, 7 would have to be a sum of 3 rational squares. But it's not. So there are no isotropic vectors. So unfortunately, the trouble with this is looking for isotropic vectors means you're trying to solve some equation with integer variables, and that's what number theory is all about. So you're going to have to use some number theory. In this case, it wasn't difficult number theory, though. They teach this in undergraduate courses, that 7 is not a sum of 3 squares. Okay. Yeah, so this is our first example that I've given of a compact hyperbolic manifold. And I'd like to make more compact hyperbolic manifold. Okay, so this is one example. Let's get some more examples. So remember, this came from the fact that 7 is not a sum of 3 squares. Well, this is a 3 manifold. I'd like to get an n manifold. But there's a problem with n manifolds. Every positive integer, including 7, is a sum not of 3 squares, but 7 is 2 squared plus 1 squared plus 1 squared plus 1 squared. 7 is a sum of 4 squares, and I guess it's Lagrange's theorem is that every positive number is a sum of 4 squares. So that means if you change 7 to something else, and you've got an x4 squared there, then there is going to be an isotropic vector. So this method of just changing the coefficient out front will not ever give you a co-compact hyperbolic manifold if you've got more than 4 variables, meaning if your dimension is greater than 3. So that's the trouble, is that we made a compact 3 manifold, but this same idea doesn't work to make a compact 4 manifold. But this is a very simple idea. Just changing that one coefficient isn't very much. So the thing you have to do is change the quadratic form in a more complicated way. But the trouble is, it's a fact from number theory. It follows from the Hasse principle, the local global principle, that if you've got a quadratic form over the integers, which is what we've got here. So suppose we're trying to make a co-compact a compact hyperbolic manifold of dimension 4 or 5 or 6 or something like that, where we'll take a quadratic form and a bunch of variables with integer entries. And since I want to have at least a 4 manifold, I need at least 5 variables there. And if I want to get a hyperbolic manifold, then when I look at the real points of the orthogonal group, I'm supposed to get SO1n. And what that means is I've got to have a plus sign and some minus signs, right? And so what that means is that there will be a vector of length 0 over R. If I want to get something, a hyperbolic manifold, my quadratic form is going to have to be of type 1n, or actually I guess type 1n minus 1 in this case. So there has to be a vector of length 0 with real entries. Well, the theorem is, if you've got a quadratic form with at least 5 variables, and it's got a real solution, it's got a real isotropic vector, then in fact it has a rational isotropic vector. So what that means is that even if you try to do something fancier, not just changing this to a 7, but no matter what you do, changing these coefficients around, include cross terms, whatever you do, you're never going to be able to get a form of type 1n with n at least, well, I'm confused, 1n minus 1 with n at least 5, and having to get a co-compact lattice out of it. This simply does not work. So what that means is, in order to construct compact hyperbolic manifolds of larger dimension, we're going to have to do something that's definitely more complicated. And I'm not going to talk about that right now, but that's what I want to do later in the lecture. At the end, I'm going to talk about restriction of scalars. That's a method that will allow us to construct compact hyperbolic manifolds. And unfortunately, I mean, they would be great if you could get them this way, but you just can't. Beyond dimension 3, you definitely have to do something else. And I guess the other thing is that I should say the other reason to do this, even if we weren't just trying to find an example of a compact hyperbolic manifold, this method will allow us to construct all of the compact hyperbolic manifolds, the arithmetic ones, all the arithmetic compact hyperbolic manifolds in, even dimensions. So it's a very important technique. It doesn't just give some examples, it actually does all of them in many cases. All right, so that's the end of the first part of the lecture. Next, I want to do something a little bit different. I want to talk some more about these isotropic vectors. And the isotropic vectors are contained in a theory called the Q-rank. So I want to explain what Q-rank means. It's an algebraic thing. I mean, like isotropic vectors are algebraic. They're vectors of, they're solutions to a quadratic form being set equal to 0. And what that has to do with something that's purely geometric, the asymptotic cone. So I'll explain what both these things mean and how they're related. That's part 2 of this lecture. So maybe I should say, we're doing something completely different. Any questions or complaints at this point? Snide remarks? Something? All right, then let's go ahead. This is the second of the 3 main topics today. I want to talk about Q-rank. I think it's something very interesting, mainly because it's really purely algebraic. It's something that all algebraic group theorists know about. But it also means something purely geometrically. You can define it geometrically as well. So let me explain what it is. But first, let me remind you what I've been doing so far. We have this condition for when G mod gamma is not compact. It's not compact if and only if there's the sequences of things or the unipotents. But today we got one that works better in practice if there's an isotropic vector that's not compact. Okay. So isotropic vectors are important. That's what I've tried to emphasize at this point. It's just people might be interested in isotropic vectors. Well, it turns out people are also interested in, so suppose we have some quadratic form Q, and then there'll be a corresponding group gamma. The point is, it's interesting to know whether or not a particular vector is isotropic, whether a vector has length 0. Algebraists are also interested not just in a single vector, but whether an entire space of vectors. So these I'm assuming to be a vector subspace of Qn. So it's a bunch of vectors. It's closed under addition and scalar multiplication. It's a subspace of Qn. Algebraists are interested in whether an entire subspace is isotropic. And what we mean by that is that every vector in that subspace has length 0. So it's not just a single vector, but a whole bunch of vectors all have length 0, and even if you add them together, you get up things of length 0. That's a totally, we call it a totally isotropic subspace, because it's completely 0 on the quadratic form. That's something algebraists are interested in. You might not be, but I'll try to get you interested in about 2 minutes. The Q rank is the maximum dimension of a totally isotropic Q subspace. That's what the rank is. It's just the biggest one of these things you can get. And let's look at an example. So suppose, for example, that the Q rank was 0. Well, if you add any isotropic vector, any scalar multiple of that vector is also going to have length 0 because the lambda comes out. If you multiply the vector by lambda, you get a lambda squared out, but lambda squared times 0 is 0. So every multiple of that vector would be 0, would be isotropic. So we'd have a one-dimensional isotropic, total isotropic subspace. If there's a single isotropic subspace, if there's a single isotropic vector, then there have to be, well, I was going to say, if there was an isotropic vector, then there would be a one-dimensional subspace. The Q rank would be at least 1. Okay. So since the Q rank is 0, there are not any isotropic vectors, and we know that that tells us it's up here, right? If this is false, then that's false. It's false that G. Well, okay, G mod would have to be compact. The corresponding symmetric space is compact, or I guess yeah, the corresponding hyperbolic manifold is compact. Q rank 0 means the manifold is compact, and in fact, conversely, compact means Q rank is 0. Right, in algebraic terms. But that's not the point. This is the start of the example, so let me just repeat what I just said. Q rank being 0, which is an algebraic condition, just says there's no isotropic vectors, tells us that the manifold is compact, and now I want to look at this compact manifold from far away. So a compact manifold looks like, I just drew a surface here, but we've got some compact surface here, that's it. When you look at it from, if you move away and look at it, it'll look smaller, it looks farther in the distance. You move farther away still, it'll look still smaller. And I didn't draw anymore, but as you go farther and farther away from this manifold and look at it, it'll appear smaller and smaller and smaller. What I'm interested in is the limit. As you get farther and farther away, this picture is getting closer and closer. This, then this, then this, then the next one will be smaller. The limit is just a single point. In the limit, all you see is a point. And the interesting thing is that the dimension of the limit, then, the dimension of the limit is just the dimension of a single point. That's 0. And coincidentally, that's exactly the same as the Q rank. Okay, so if the dimensional limit is 0 and the Q rank is also 0, and I said coincidentally, but the point is it's not a coincidence. The dimensional limit is always the Q rank. That's a theorem. Okay? But before I state that theorem, let me say that this limit, I've been calling it the limit as you go from a large distance. That's definitely not a very good technical definition. That thing is called, that limit is called the asymptotic cone. The asymptotic cone of any metric space can be defined. It's the limit as you look at the metric space from farther and farther away. But technically what we do is we take a limit, just let t be the distance away you are. As you go away, you use the same metric on your space, but you scale it by a factor of t. That's the same as getting a larger distance away. And technically it turns out you have to fix some base point also, because otherwise as you're going away, if you're shifting your point of view back and forth, then it's going to be nonsense anyhow. But that's it. That's called the asymptotic cone of the metric space. So really, what I said here is that the dimension of the asymptotic cone is the same as the Q rank, at least in this example. And let's look at another example, and we'll see that we get the same thing. Okay, so for another example, suppose we're in the case where I think people in this room might be interested. Suppose we're talking about we're trying to make a hyperbolic manifold. So gamma is an SO1n, and let's suppose that the quotient is not compact. If we had a compact manifold, the Q rank would be 0, the asymptotic cone would be a point, everything dimensions would be 0. Okay, so let's check the non-compact case. Well, in that case, you people know this better than I, a finite volume hyperbolic manifold has a bunch of cusps, finitely many cusps. So that's my picture of a hyperbolic manifold of finite volume that's not compact. And now if we look at that thing from a distance, well, those cusps still go off to infinity. They don't disappear, but the core, I guess you call it, is getting smaller. And in the limit, I can't even see the core there anymore. Right? If you go farther and farther away, you'll get these cusps, these things are going off to infinity. They get thinner and thinner as you go off to infinity, as you get farther away, but they're still infinitely long. So the limit is just going to be, you can call it a star. It's just finite many rays coming out from a single point. That's the asymptotic cone of this space. And the dimension of this, I call it the limit, yeah, I could call it the asymptotic cone. So the asymptotic cone is just finite many rays. The dimension, obviously, then is 1. And it turns out that is exactly the same as the Q rank. The thing is that since the space is not compact, we know the Q rank is not 0. There are isotropic vectors. But the thing is that we're in SO1n, there's only one-dimensional space of real isotropic vectors. That's because it's a signature 1n. That means that you can't get two you can't get a two-dimensional isotropic subspace. I don't say it. There's only one plus sign, and the rest are all minus signs. You can't get two independent isotropic vectors. Okay, so even over the reals, the real rank is only one, and the Q rank is going to be smaller because you're looking for rational entries. You're not allowing all real entries. So anyhow, maybe it's not obvious, but the Q rank in this case is one. So the asymptotic cone has the same. The dimension of the asymptotic cone is exactly the Q rank, and this is true in general. It's a theorem that whenever you've got a locally symmetric space of finite volume, the asymptotic cone, the dimension of the asymptotic cone is exactly, it's a simplicial complex, and in fact its dimension is exactly the Q rank. So we define the Q rank algebraically, but in fact you don't need to be an algebraic to figure it out. If you're a geometer, just look at the space from a long distance, and whatever dimension you see, that's the asymptotic cone. And maybe at this point let me mention also why it's called the asymptotic cone. So in fact, well, I'll say a little bit more about this in a minute, but if you look at this thing here actually is a cone. If you take 3 points at infinity and then cone, and then 1 point that you're going to cone from, so I've got 3 points, and then I pick another point to cone from, the cone on that 3-point set is this asymptotic cone, and that's what's always going to happen. The asymptotic cone, there's some set out at infinity, and you take the simplicial cone on that, or I don't know what you call it, whatever you call it, but anyhow, it's not suspending it, but take the cone. That's what the asymptotic cone will look like. And the question is just what kind of a set do you get at infinity? And in fact, well, Hattori's theorem just tells us what the dimension is, but in fact we can do better. In fact, I can tell you not just the dimension of the asymptotic cone, but an algebraic geometer can tell you what the asymptotic cone exactly is. It's a cone on some set, and in fact that set is what's called the Tietz building of all the parabolic subgroups of G. So it's an algebraic thing. It's okay if you don't understand this, but the fact is that the algebra will act, if you understand the algebra of G, you can figure out exactly what the asymptotic cone is, but even if not, you might be interested in just knowing what the asymptotic cone is basically. And I don't know, maybe you think it's not interesting to look at a manifold from a long distance, but actually the asymptotic cone is telling us something more. It's a very nice space. It's a very simple, simplicial complex that is closely related to X mod gamma. And in fact, it's not just something that you see from a distance. Gamma mod, X mod gamma is just its asymptotic cone up to quasi-isometry. So if you're interested in quasi-isometries and you want to throw out the part of your manifold that doesn't matter, just pass the asymptotic cone. That's the smallest dimensional simplicial complex that will give you the right quasi-isometry type. So it's the asymptotic cone of the Q rank actually gives you information about the quasi-isometry type of your space. And let me just mention, so that's my motivation for why Q rank could be interesting. That's all I'm going to say about Q rank, that it tells you something about the asymptotic cone. But let me mention one more thing about it before I quit. Another reason Q rank is important to geometers is that it tells you the cohomological dimension of your space. The cohomological dimension of gamma. Well, first of all, if our manifold was compact, then the cohomological dimension would just be the dimension of the manifold. So in the compact case, we'd expect to get just the dimension of the manifold, or the dimension of the universal cover. Okay, so this is what you get if your manifold's compact. When it's non-compact, then definitely it has to go down, and the more non-compact your manifold is, the farther down it should go. Well, we have something that tells us how non-compact our manifold is. That's the Q rank. The more non-compact the manifold is, the bigger it'll look when you look at it from a distance. So in fact, the difference, what you have to subtract off, is exactly the Q rank. Okay? Yeah, so the cohomological dimension of an arithmetic group, it's the obvious thing minus some defect. The defect is exactly this Q rank. So that's another way to calculate Q rank. What's another application Q rank? Except for the experts in cohomology know this and right. I'm assuming here the gamma is torsion free. Otherwise, the cohomological dimension would be infinite. Okay. That's okay. Yeah, that's the end of part 2. I'm going to get into part 3. I'm going to talk about how to actually construct co-compact lattices in SO1n with n bigger than 3. This is where we're going to need restriction of scalars and other things we've talked about. So I think this is a good time for our break. Let's take 5 minutes.